So today I'm going to talk about how we can keep the lubricant into the slippery liquid infused porous surfaces, which is usually called slips. So this work was done by Henri Tran, which is a PhD student that is supervised by Leonie and me. So basically, when we are talking about repellent surfaces, we mainly think about super hydrophobic surfaces, like this one. Okay, so on super hydrophobic surface, you have a droplet with a spherical shape like a bubble, and usually the droplet will roll off the surface when you just have a very small tilting angle as compared to the horizontal plane. Okay, but the main drawback is after a while, you are moving from the so-called KC state, where the droplet is just staying on top of the surface, to the Benzel state, where the droplet is strongly grafted to the surface. So a way to prevent that is by doing more complex surfaces, like structure with the so-called rear entrance morphology, something like looking like a mushroom, or maybe more a complex one like doubly rear entrance, or you can stack them in order to do something like that, which is multiple rear entrance structures. So as you can see on this image, we can do that. But in this case, for instance, it was made by a 3D direct writing lithography, which is based on a lithography technique. We made some very nice LCM picture, but as you may understand, it's not easily scalable. So another approach is to start with a porous material, lubricate it with a repellent liquid, which is liquid B in this case. And when you put a droplet on top of this slip surface, so if you tilt it or just vibrate it, so the liquid will slide onto the surface. So liquid A will slide onto the surface. So the main drawback is the lubricant depletion of the surface. So after a while, there is not enough lubricant and the water droplet will stay stick onto the surface. So this lubricant depletion mainly comes from what is called a wetting ridge. So there is a ridge here in between the lubricant and the water droplet. And this ridge may also fully wrap the water droplet. On this picture here, you can see the growth of the ridge over time, and it's in static case. But if the water droplet is sliding, even if it's slowly sliding, you can see there is a strong increase in the size of the ridge. And due to that, there is a strong lubricant depletion. The way to see that is on this picture where the droplet here is moving downward, and you can see the trace of depletion, lubricant depletion behind the droplet. So our approach was to make different kind of porous materials based on nanowires, zinc oxide nanowires. So we know how to do like vertical nanowires, tilted nanowires, or very strong entanglement of nanowires. Okay, and in this case, we call that random nanowires. As lubricant, we have chosen silicone oil, and for the lubrication, we decided to not use a standard method like spin coating, but using the capillarity. So we just put in contact our sample with the silicone bars and wait for the growth of the film inside the porous structure. So here you can see on this graph, from moving to bottom to top of the structure, the rise is quite long when we have vertical nanowires. It's almost 2 hours. When it's just around 40 minutes when we have tilted nanowires, and less than 20 minutes in the case of the random shaped array. So, and if you look at the silicone oil, you can see it's smooth because we have a coated layer of silicone oil onto the nanostructures for the vertical and tilted nanowires. While it seems to be very rose and with a conformal coating in the case of the random nanowires. Try to compare our techniques, so our carrier lubrication, to the standard one like spin coating lubrication. For here, for different kind of nanowires array, you can see that the wetting ridge is higher, is bigger in the case of spin coating than in the case of carrier lubrication. And you can see here, when we change the morphology from something vertical to random one, there is a decrease in the size of the wetting ridge. And here you can see we can no longer see the wetting ridge. So it seems that we find a way to decrease the wetting ridge and the lubricant depletion. So now, okay, on a dynamical point of view, what about the trace when we have liquid droplets moving on the surface? Here you can see there is a trail for the vertical nanowires, and this trail is decreasing for the random tilted one, and there is no more trail for the random nanowires. So it seems that there is no lubricant depletion. And the next question is, are these kind of surfaces are robust? So we just try to put some droplets dropping onto our surfaces and see if they are sliding. So here you can see that for the random nanowire, there is almost 23 droplets that slide, and after the 23rd one, they stop to slide. So it's just 13 in the case of tilted nanowires and just 9 in the case of vertically aligned nanowires. Then we leave our surfaces for just 5 minutes, waiting for 5 minutes, and we start the same experiment exactly at the same position. And for the random nanowires, we have exactly the same amount of droplets sliding before stopping to slide. So there is a strong decrease for the tilted one and a very, very strong decrease for the vertical one. And after the third cycle of experiment, we saw exactly the same amount of 33 droplets for the random nanowires, where it's just 2 for the tilted one, and they are just stay still for the vertical aligned one. So it means that we have a strong lubricant retention in the case of the randomly aligned nanowire, and there is a kind of self-healing effect, but we just have to wait 5 minutes before the sliding effect. So briefly, in conclusion, we developed a facile approach in order to make slip surfaces that it's easily scalable, and we found that we have a strong lubricant depletion resistant slipped material with some self-healing abilities. And what we is working on right now is what is the anti-fouling behavior of such kind of surface. So thank you for your attention. You have question? Time for question? Yeah. Questions.
Random structures.
Sorry? Oh.
How did you grow the random structures?
So it's just by.
Could you repeat the question?
Okay, so the question is how we do the nanostructures, how we grow
random structures.
the random one. So it's a chemical bath deposition technique, and key point is we preheated everything and adjust all the parameters. So it's almost the same chemistry for the 3 kind of structures. But the main difference is how we do that, what are the different steps, and the difference is in the seed layer, because there is a seed layer in order to grow the nanowires. Okay.